You're about to listen to a new episode of Audio Signals. Get ready to take a journey into the known, the unknown, and everything in between. Recorded at no specific point in time nor space, ITSP Magazine's co-founders Marco Ciappelli and Sean Martin follow their passion and curiosity as they venture away from the intersection of technology, cybersecurity, and society to discover new stories worth being told. Knowledge is power, now more than ever.
Nintex is the global standard for business process management and automation. The Nintex platform helps their clients accelerate progress on their digital transformation journeys by quickly and easily managing, automating, and optimizing business processes. Learn more at nintex.com.
Blue Lava is the first business platform for CISOs to manage their security program. Blue Lava guides security leaders to effectively measure, optimize, and communicate their security program with confidence and ease in one platform. Learn more at bluelava.net.
Marco,
Sean,
do you hear the signal?
the audio one?
The audio one, the quattro, quantum,
The quantum signal.
quantum signal. I don't know where quattro came from, but anyway.
Is that such a thing, or you just
Quattro
made that
quantum.
up?
Quattro quantum, I don't know. I'm making stuff up.
You know why we're making stuff up is because today on Audio Signal, we're starting this series that I was like, I always say you just can't know everything about everything. That would be too presumptuous. And many times I just don't know anything about a lot of things. And and we get requests to come on the show from people that are really knowledgeable about things, especially in science and research and in a lot of field, honestly. And I said, I want to have this conversation, Sean, because we expect our audience to leave our conversation with questions and to be interested in something. And you got to start somewhere.
You have to start somewhere. So I started over there. So I'm not pointing to anywhere, but
So
no,
are you making a quantum joke already?
I started in the place that you can't see because you're looking at it.
I see. I see. You're already.
People are like, what the hell is he talking about?
Now, you know what? I'm going to tell you this, and then I'm going to move the conversation with our guest. When you read a little bit of an introduction to like what is quantum, and you hear these words like superimposition, interference, entanglement, and it sounds to me like it's magic, and that's often what they say. If you don't know what it is, many times it sounds like it is magic, and people sometimes are afraid of it. So let's see if we today talk about quantum computing, but we start from the beginning, understanding maybe what quantum is for a person that doesn't really know that much about that. And guess what? We brought someone to do that, Sean.
You're not going to rely on me this time.
No, sorry, man.
Thank goodness.
No. Cybersecurity, yes, but not for quantum.
Well, let's bring Doug in.
Let's bring Doug in. So our guest today is Professor Doug Tougaw, and we are excited to talk to you. I'm not sure about what, but
I'm excited too. I'm looking forward to it.
Why don't we start from the beginning? A little bit about yourself. I already break the fact that you are a professor. So what do you teach? Where do you teach? And how do you get there?
I'm actually the Dean of Engineering now at Valparaiso University. I have been teaching in electrical and computer engineering at Valpo for the last 25 plus years. Before that, I was in graduate school where I began to study quantum mechanics and quantum computing. And I've been doing that research for nearly 30 years now. So it's been an exciting time. Back in the 90s, we would say, by the time 2020 gets here, we'll be able to do these things. And 2020 has already come and gone. So now we're able to do some of the things we've been planning to do for decades.
And what are those things?
Well, it's to me, it's the future of computing. It's computing that's based not on traditional physics, but on quantum physics, quantum mechanics. It's kind of like there are three domains of physics. There's the physics of our normal world, of things that are about the same size as us, and and that move at about the same speed as us, sometimes considerably faster, but not as fast as, say, the speed of light. Then there is relativity. That's the study of things that are very, very large and things that are moving very, very fast. And that has really its own type of physics. And then there is the study of things that are very, very, very small. And that's the study of things that involve quantum physics or quantum mechanics. And so what we find is that as we begin to design computer chips, the computer chips work really, really well as they're sort of our size and as they get smaller and smaller. But eventually they begin to impinge upon the domain of quantum mechanics. And then weird things begin to happen. The rules are just completely different. And our common sense, which has been developed by the physics of things that are about our size, begins to just fail. And so what we find is that quantum mechanics can be a real challenge for these sorts of computing opportunities once you begin to shrink the circuits down much, much smaller. But the benefit of quantum computing is that it actually uses those quantum mechanics rules to be able to do the actual calculations. So rather than opposing them, they use those rules. It's sort of like, if you tried to play football on an ice hockey rink, it would be very bad. It would be horrible. But if you put ice skates on, all of a sudden now you've got a whole new sport, a whole new game. And so by using quantum mechanics rather than trying to oppose it, we're actually finding that we're in a whole new game.
Wow, so many questions already. I'm gonna go with the first. You kind of touched on it, but I'm still wanting to know more. The difference between quantum mechanics, quantum computing, quantum physics, and I don't know if there are other quantum terms that we should be aware of. And what's the connection and relationship between those things? I think you said computing uses the rules of mechanics, but what's that landscape look like?
Absolutely. So I guess I would say that quantum physics is really just another word for quantum mechanics or vice versa. Those two are largely interchangeable, at least from a layman's perspective. So it's really just the laws of physics at a very small scale. And then quantum computing in its various forms. There are many forms of quantum computing, and they all are really just computing using computer chips that are based on the rules of quantum physics. So taking advantage of the very odd behaviors we see for very, very small things.
So let's backtrack 1 second, and then I'm sure the focus is going to be on computing and what is the future and what it will allow us to do. But if you had to explain quantum physics to, as they used to say, to grandma or someone, and how would you present that? Because it really tough to grasp. I mean, I read, I try to understand. I read, Einstein biography, and then what happened after that. But my mind is not that kind of science. So, how can we grasp it as an everyday person interested in it, of course, and say, okay, I get it. At least I know what it is.
Yeah. So as you say, it is. I've probably taken a half a dozen classes in quantum mechanics that I've been doing research in this area for 30 years, and I'm not sure that I still completely understand it.
It's like the metaverse. We don't know.
There are maybe a dozen people in the world who really completely understand quantum mechanics. I'm not one of those dozen people, but I'll do my very best. In our world, things are very certain. I know how large an object is. I know where it's located. I know how fast it's moving. But at the very, very small scale, those things are much less certain. I can't really say with certainty exactly where an object is. Or if I say where exactly where it is, I can no longer say exactly how fast it's moving. So there's this uncertainty principle that says that we don't really know both where it's located and what its momentum is. There is also lots of very complicated interactions among the particles. And those complicated interactions are the best part, because they're the reasons why quantum computing shows so much promise. But I'll also say that the particles at the very small domains, they behave very strangely. So for example, I can have a particle that is inside of a wire, and then an instant later, it's inside of an adjacent wire. And at no point in time was it in between those two wires. That's known as quantum tunneling. And my brain doesn't really accept the fact that it can be in one place and then it's in another place, and at no point was it in between those two places. But physics doesn't care what my brain thinks. Physics just works. And so we have to accept that it has been measured, it has been demonstrated dozens of times that this is the case. And we have to try to find ways, even if we don't truly absorb and internalize the ideas, we can use them. We can use them in very effective ways to do very interesting calculations.
Mm.
And is that the goal? You said calculations, because I'm trying to figure out what we're trying to do here. I'm going to take a second because you talked about uncertainty.
Yes.
I remember early in my program management days, this concept of ambiguity. You don't know what something is. Looking at building a product, let's say, there are many things that can play a role in how well or how fast or how on time or on budget you can build something. So this ambiguity of something can change. If you embrace that and be prepared for the change, I can foresee an end goal, right? And kind of manage to that. Is that the purpose of embracing the uncertainty in quantum computing, or is that even messed up in my mind that's not what we're trying to do? Trying to control an endpoint.
That's a very apt analogy. I would say another very special thing about quantum mechanics is that every single time you try to measure something, you change it. And that's a perfect analogy to management, that when you measure something, you change the behavior of the thing that you're trying to measure. The same thing is true of an atom or a molecule or an electron. Every time that I measure it, it changes its state. So, for example, there might be a region of space where this electron could exist. But as soon as I measure exactly where it's located, then it's exactly there. But until I measure it, it could have been any of those places. It could have been anywhere within that range. But once I measure it, now it's locked into that location. Now, if I let it then evolve and move back to its normal state and don't pay attention to it, then it will spread back out again and it'll be in that region. If I measure it again, it could appear somewhere else. But once I measure it, it has changed. But another thing that I think you tied into is sort of the difference in philosophy between a scientist and an engineer. A scientist, their goal in life is to understand the world, to understand the laws of physics, or to understand how biology or chemistry or whatever science you're studying, how that works, and to be able to push back the darkness, to be able to push back the frontier of knowledge so that we know more about exactly how the world works. And that is a spectacular calling. An engineer's calling, though, is to build on top of that and do something useful with that knowledge. So the engineer takes the work of the scientist and then applies it to create something new that performs a useful task. And that's really what we're focusing on. So whereas physicists are focused on understanding how the world works, engineers are focused on making the world better. And so we see quantum mechanics as an opportunity to build something new that can do something that is incredibly useful in a very effective sort of way.
You know, that remind me also, what coming from sociology, there is this thing that when you tell somebody you're studying their behavior change. So there you go. I mean, we're using our brain, we're using psychology. We still don't understand how that works. But
right.
According to what you said, that doesn't mean that we cannot apply it.
That's right. There's actually maybe the most famous experiment in all of quantum mechanics is called the double slit experiment, where if you are observing the particles, they behave one way, and if you're not observing the particles, they behave a very different way. This experiment, boy, again, it's one of those I just can't seem to get my mind around, but it doesn't matter because it works. And so we try to find ways to use it to do useful things.
It's kind of like let it go.
Just exactly. Yep. You have to sort of leave your common sense on a shelf and just apply what has been measured.
Yep.
So, and then I guess in general, that's probably hard to do, but then I'm trying to figure out, well, do we have to leave our understanding of the world on the shelf as we try to figure out what we're trying to accomplish with quantum? Well, you mentioned a world of quantum. I'm wondering, is that a space we enter into because it operates differently than what we're used to, and then we leave that world, or is there a connection to the physical world where physics we understand apply? How does that connect?
Yeah, that's a great question. Two of the biggest challenges of using quantum computing are getting the inputs into the quantum device and then taking the outputs out of the quantum device. And both of those challenges lie right at that domain of we're getting into an area that is very quantum mechanics based, but we're coming from a conventional processor, and then we're at the output, we're taking them out of a quantum device and moving them into a conventional processor. So you're right, those boundaries, domain changes or domain boundaries are always the most challenging part of a design project, and that's really what's happening here as well.
So this is all fascinating, and I think it's very philosophical too. So I can totally go there. But I would like to know, all this that I don't understand it, but I can control it, which is kind of what we do about a lot of things in,
Yes.
in natural science as well. What are the applications of quantum computing, and how that change what we're already doing with computing? I mean, I know faster calculation, way faster calculation, and then what?
Yeah. So it's really interesting if you kind of think back to, well, I wasn't here, but in the 1950s, when computers were just sort of beginning to emerge, there were some problems that were very quickly accepted as being, oh, this is ideal for a computer to do. Calculating, for example, ballistics tables when we're choosing how to launch a missile, not a missile, but a projectile. That was one thing that computers were very good at. Also, doing things like census calculations, where there are huge numbers that need to be added together. These were very early sorts of problems in the 1950s for the very first computers. And they were selected not because they were necessarily the most important problems, but because they were the problems that were the best fit for the technology. And the same thing is happening in quantum computing as well. There are the analogies between the 1950s with conventional computing and the 2020s with quantum computing are very, very similar. In both cases, there's a new technology that is the capacity, the future potential is practically endless, but it's still in its infancy. And so we begin to look for problems that are a good fit for the technology, even though it's in its infancy. And there are some that have immediately come up. One that I'm certain will be of interest to your listeners is cryptography. RSA algorithm and maintaining cybersecurity is certainly one of them. Search problems is another one. If I told you that, for example, there are 1 billion of these boxes, and inside of one of those boxes is a prize, but you have to search and find the prize. Well, ordinarily, you would expect to have to open about, on average, 500 million boxes, and maybe as many as 1 billion boxes to find the prize. But because of the weirdness of quantum computing, it can actually do it in sort of the square root of that number. So it can solve it much, much more quickly. Simulations, especially simulations of molecular systems, drug design, computer-aided drug design is an important possible application. Genomics, improving the speed with which we can sort of study the genome of a living being. Machine learning, data mining. These are all applications where there are likely to be huge steps forward, or in some cases maybe backward, due to the power of quantum computing.
Now, I'm trying to connect the dots here. So maybe we can focus in on the healthcare examples, perhaps. So I guess physics and engineering, connecting those two things together in the traditional world, not in quantum.
Yes.
We're bound to the way we think. We're bound to the physics of the computer and the way that it works. And I don't know, what's you mentioned embracing the uncertainty and kind of throwing away our logic, if you will, in the quantum space. And you said kind of the square root of the time it takes. How does that help create new things? And maybe, I don't know if you can describe the scenarios in the medical space, or one scenario in the medical space to help.
Yeah, let's take the medical space as a great example. So anytime now that we're looking at doing drug design, we're basically looking at very complicated molecules, and those complicated molecules will often twist and form themselves into very complicated geometries, and those very, very complicated geometries are very difficult to calculate, to the point where these drug manufacturers will often have supercomputers that can help to model the devices, model the molecules that they're designing. And quantum computers could do those much, much more quickly. More generally, I guess I would say quantum computers don't don't enable a whole new type of calculation. They enable calculations to be done much, much, much more quickly. So anything that can be done
Is that because that's just because we're bound to our understanding of it? Because I'm trying to think, can it do calculations that we can't even fathom?
Yep, it's so difficult because it's such a complicated topic. But there are kind of two main things that quantum computers have in their advantage over conventional computers. And the first of those is superposition. So superposition means that rather than a binary state where this particular bit is either a 1 or a 0, which is kind of the way that all of modern conventional computing works, superposition simply says I can have a 1 or a 0 or anything in between with different probabilities. So maybe it's probably a 1, but it could be a 0. Maybe it's probably sort of halfway between a 0 and a 1. And it's even more complicated than that because it can actually be a complex number. So it is actually two numbers. So rather than thinking of I either have a 1 or I have a 0, you could think of it as like a square. And inside of that square, there are different places that are more likely for the measurement to be made than other places. But there are also places that even though it's unlikely, it could be measured in that state. So what superposition really does is it gives us the capability of having more complicated answers. You know, when you're talking to a 5-year-old, the world is very black and white. People are good and bad. Things they're delicious and they're not. But as you get to be an adult, you realize things are more complicated. And in the same way, superposition simply means that things are more complicated. We don't have a 1 and a 0. We have a combination of probabilities of 1s and 0s and really everything in between. So that's one of the two special powers of quantum computing. The other one is what we call entanglement. And entanglement means that you can take these quantum devices, we call them qubits, Q-U-B-I-T. So these qubits, each one of them holds one quantum state, that little square that I was talking about. But if I put two of them very close side by side, I can connect them together quantum mechanically. That's known as entanglement. And then I don't really just have two, I have a pair. And that pair is more powerful than the two combined. So it's again that the sum is more than the total is more than the sum of its parts. And I can go beyond 2. I can have 3 or 4. Imagine if I had 5 qubits or 10 qubits. Now I'm combining these together in a way where they are much, much more powerful than even 10 individual qubits would have been. Sort of like the players on a team. They're working together to achieve a goal. They could definitely, and if their team is cohesive, we call it coherent. If the team is coherent, then they're going to be able to accomplish much, much more complicated tasks.
Wow. Let me ask you something, because this is all fascinating. I remember 15 years ago, maybe, was a good friend with a scientist, a quantum scientist. And he was doing research on quantum computing with a company called D-Wave in Canada, I believe. And he was always telling me his biggest problem was to control the environment. So they knew what it could do, but they were working on, I don't even remember, like he was showing me like the circle where the quantum is active, and I'm being very ignorant here, freezing it, or I remember it was bringing me an example, and it's like, yeah, we're almost there. So the question for you is, are we there yet?
We're almost there.
Almost
to an extent, we're there.
Damn it.
Do we know?
I think, well,
as soon as you check to see if you're there, it's different. You say.
Are we there and over there?
We're in between. So there are of course a couple of really big companies. Google and IBM are the two biggest leaders that I'm aware of, and then just hundreds, thousands of startup companies that are all working in this same area. The biggest quantum computer that I've heard of is 127 qubits, and 127 qubits is pretty remarkable. That's from IBM. At 100 qubits, it would be equivalent to the fastest regular computer. So already they have a computer that is faster than the largest regular computer. If you can get to 1,000 qubits, it can solve problems that are beyond any modern computer. And I just heard a presentation from the CEO of IBM. They said that they expect to be at 1,000 qubits within 2 to 3 years. So within 2 to 3 years, they'll be at a quantum computer that can solve problems better than any non-quantum computer. And at that point, we begin to think, what is the future? When will we transition from regular computing to quantum computing? If we can go beyond 1,000 qubits, now there's a lot of challenges, and we'll talk about those challenges, but if we can go beyond 1,000 qubits to 10,000 qubits, 100,000 qubits, the future is really remarkable. If again, going back to the 1950s, if you would have told someone in 1950 that we would have a chip that had 100 billion transistors on it, they would absolutely not have believed you. And in the same way, if you talk to someone today and say, can you imagine a world in which there'd be a chip that has 10,000 qubits on it? They would say, heck no, there's no way that's going to ever happen. Well, nothing is more likely to happen than if you tell an engineer that something is impossible. That is a great way to motivate them to work hard.
So talk to me about some of the technologies, because you're talking about chips, and the first thing that comes to mind is the GPU. I'm just wondering, are there overlaps in technologies? Can I run a quantum computer on my MacBook, or does it require a special computer with certain types of chips? What's that technology landscape where things begin to overlap with quantum and other stuff?
Yeah, it's a great question. The short answer is no. Unfortunately, the computers on our desktops can't do quantum computing. They can simulate quantum computing. That's what my research does, but they can't actually perform the quantum calculations. But the devices that are used to fabricate our laptop and desktop computers can also be used to fabricate quantum computers. So we're now already down to the place where we can fabricate electronic devices that are on the scale of a couple nanometers, and that's, now we're talking about maybe something that is the width of 20 atoms. So if I often think of the boundary as being about 1 nanometer, about 10 atoms. That's when we get into solidly quantum mechanics domain. So if we were to stop producing, not that we would, but if we were to stop producing regular computers, we could use those facilities to produce quantum computers as well. By the way, there are probably 30 or more competing different ways to produce quantum computers. And we'll have to wait and see which one's going to turn out to be the best. There are two that seem very popular right now. There's superconducting qubits. And so these are the ones that are made on sort of traditional technology. They're sort of based on the same manufacturing methods that we've been using for many years to make modern computer chips. And then there's also something called trapped ion. Trapped ion is very different. This is where we take very complicated molecules, could be yttrium or something like that, and put them into a magnetic field that can hold them in place. And it gets more complicated if you're talking about a trapped ion, but on the other hand, there are some things that make it very, very promising as well. So there are traditional quantum computers that we can build using traditional methods, and then there are others that are a little bit more out there, but have a lot of things that sort of speak in their favor.
So let's stick with this for another moment. So there's the computer, and it can do stuff, but it has to be told what to do. So the programs, the applications, I presume it has data storage necessity. I don't know if that requires offline storage as well. What does that world look like? And are we kind of there? Do we have all those parts in place, networking and all the other stuff that goes with it?
So we actually have quite a lot of that in place. Fortunately, this is a problem that we've been working on for about 30 years now, or 40. I've been in it for 30, but it's been around for longer than that. The programming, I don't want to use the word programming because I don't want you to think that this would be done in Java or C++ or something. It's going to be a completely different type of programming, but it's still that capability exists. IBM actually has a quantum computer that they allow people to program, and they run thousands of simulations, not simulations, they run thousands of, they call them circuits every day. And so the tools are available. They're open source right now. They're currently free to run. You have to apply, but once you've been approved, you can run your quantum circuits on an IBM quantum computer. There are challenges, as we mentioned. Getting the data into the quantum computer is challenging. Getting the data out is challenging. There are some other challenges too, but yeah, a lot of the tools are already in place right now. It becomes a challenge of increasing the size and scale of the quantum computers to be able to achieve our goals.
All right, so we have artificial intelligence. We talk about general artificial intelligence. Some people say it's the end of the world, apocalypse taking over. We're all going to be submerged by paper clips and stuff like that. And then we're not getting there because the computer needs to be more powerful. So quantum computer seems to me one of those superpower that comes with a lot of responsibility.
Yes.
Right. So I'm envisioning that if you put together artificial intelligence and quantum computing, you will be building some kind of a monster. So let's talk about kind of as we close for this episode, because I have a feeling there's going to be more pro and cons of what could bring if we cannot control it. Breaking encryption, it's one of the first come in my mind, and passwords at that point is like, yep, no, whatever. The door is made of paper. I'm just going to bring it down. Other things like that you're excited about, and other things that you may be a little concerned about. We need ethics here.
Yeah, I think any engineer with a conscience is concerned about the possible applications of the work that they do. I know that we spend a lot of time here at Valparaiso University teaching our students about being concerned about the ethical implications of their work. And I think that certainly is the case here. In the same way that there are ethical implications of conventional computing. The ability to communicate widely with a broad audience seems at first like it would be a unilateral good, but there are drawbacks to it as well if what you're communicating is false. So you have to think about what are the implications of quantum computing in particular. You already identified the first one that comes to mind, which is that there are going to be some serious repercussions to cybersecurity, cryptography, passwords. Those are all going to become much more challenging. Machine learning and AI is another big challenge that I think that we need to give a lot of thought to. I know that's not really the area where my research focuses on, so that isn't one that I've given a lot of thought to. But I know that there are people who are definitely giving that a lot of thought.
Speaking of thinking, I mean, we've examined this, so now we've changed it, and it is our perception of quantum computing. Hopefully we've done that job today. Yeah, I mean, there's no question we can continue down 20 different paths and have an equally long conversation along each path. I think today we got a nice overview of what it is, what's possible. I don't know that we have an answer of when. And many other questions I'm sure remain unanswered. I think the interesting thing for me, having an engineering mindset and a programming mindset, is that there are systems available to play with. IBM is the one example you gave. I think that's cool. I think for people listening that might be interested in this topic, they probably already know more than I do if they're interested in it. But the idea that there's a place they can go to explore and to see what's possible. And perhaps, Doug, you can share some of your work and some of the work that maybe some of your students have done, or other projects that you think folks listening to this might be interested in and find useful to explore more. And we'll ask for you to share some of those with us offline, and we can include those in the show notes for folks to follow up with.
Absolutely.
Yeah, as a matter of fact, we didn't actually get into what you specialize into the research, which is the quantum cellular automata. That's what it is.
That's right.
And it's funny because when we talked about this conversation, I was like, I probably would love to have this conversation if I had a clue of what that is. So I think we can leave it for a next conversation. And I really enjoyed this one. Sean is the engineer mind. I'm more like the storytelling. So I just look at quantum as I look at magic. It's fantasy for me, but it's a great story, and I know it's real. So don't get me wrong. I know it's real. Sean, I had a lot of fun. I think we both agree that we should have more conversation with Professor T.
Yes, absolutely.
So please come back. We'll plan on that. But first of all, we invite everybody to listen to this. Of course, if they got here, they already listened. But who knows? Maybe they're at the beginning now.
Listen to it again.
How do I know? Maybe they're listening to this and to another one at the same time. And if you guys have questions, let us know. Post it on the social media. Maybe we'll ask Doug next time. So I'd like to know that there's people that get excited about this stuff as we do. So thank you very, very much.
Yeah, thank you, Doug.
Thank you.
Blue Lava is the first business platform for CISOs to manage their security program. Blue Lava guides security leaders to effectively measure, optimize, and communicate their security program with confidence and ease in one platform. Learn more at bluelava.net.
Nintex is the global standard for business process management and automation. The Nintex platform helps their clients accelerate progress on their digital transformation journeys by quickly and easily managing, automating, and optimizing business processes. Learn more at nintex.com.
We hope you enjoyed this episode of Audio Signals. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society, and some even beyond that.